We continue to learn Chapter 6, Eigenvalues. Section 6, Quadratic Forms. Part 2, Quadratic Surface. Now we consider quadratic surface. The graph of a quadratic equation in 3 variables is called a quadratic surface. There are 4 basic types of non-degenerate quadratic surfaces. So the first one, ellipsoids. The second one, hyperboloids of 1 or 2 sheets. The third one is cones. The fourth one is paraboloids, either elliptic or hyperbolic. So ellipsoids, its equation is like this. So x power 2 divided by a power 2 plus y power 2 divided by b power 2 plus c power 2 divided by c power 2 equals 1. And a greater than 0, b greater than 0, c greater than 0. So this is ellipsoids, just like this figure. So you can see the range of this x, y, and z, right, of this figure. You can see the symmetric property of this ellipsoids. So ellipsoids is symmetric with respect to each axis, also to the xoy plane, xoz plane, and the yoz plane. And the special case when a equals b equals c. So this is a ball, right? When a equals b equals c, you will get x power 2 plus y power 2 plus c power 2 equals a power 2, like this. Okay, so you can see some conic sections. For example, you choose z equals some special value, and then you can have its intersection with this ellipsoids. You can get, for example, ellipsoid. You can get ellipse, right, as its conic section. So if z equals 0, you will have this ellipse, x power 2 divided by a power 2 plus y power 2 divided by b power 2 equals 1. So if y equals 0, okay, if y equals 0, you can get also an ellipse with mathematical formula here. And if x equals 0, you will also get the intersection as a conic section ellipse. Okay. Now we consider another type of quadratic surface. We call it hyperboloids. So hyperboloids, if it's one sheet, it's like here, the mathematical equation is like this: x power 2 divided by a power 2 plus y power 2 divided by b power 2 minus z power 2 divided by c power 2 equals 1. The range of this x, y, and z is not like the ellipsoid we mentioned before, right? They are bounded, right? So x, the absolute value is no more than a, right? Y absolute value is no more than b, and z absolute value is no more than c. However, for this hyperboloids, you can see for x, so for x, it can tend to infinity, right? For y, it can also tend to infinity, right? For z, it can also tends to infinity. And here, from this equation, you can see that x power 2 divided by a power 2 plus y power 2 divided by b power 2 equals 1 plus z power 2 divided by c power 2 is greater than or equal to 1. So here, you know, from here it should start from this one and then extend, right? Extend to larger, like larger ellipse. So the symmetric property we consider now, it is symmetric to x-axis, to y-axis, and z-axis. If you put x equals minus x, you will get the same equation. Right? So it's symmetric with the x-axis. And how about xoy plane? It's also symmetric, right? If xoy plane, then right, you can also get it as symmetric. How about yoz plane? Yoz plane, the figure is also like symmetric, right? XOY, XOZ. How about YOZ plane? Also symmetric, right? So it's symmetric to the planes and also to the axis. And now we see the conic sections. If Z equals Z0, if Z equals Z0, so we put here is Z0, you can get this conic section. So this conic section is an ellipse. Okay, so you use this plane Z equals Z0 to intersect with this hyperboloids, you can get this ellipse. And if you use x equals x0, x equals x0 to intersect with this hyperboloids, you can have this conic section. So see this conic section, this is a hyperbola. See, hyperbola. So as its conic section. Okay, hyperboloids has also another case is two-sheets hyperboloids. Two-sheets hyperboloids is like here. So it's x power 2 divided by a power 2 plus y power 2 divided by b power 2 plus minus z power 2 divided by c power 2 equals minus 1. So here is minus 1. The one sheet is positive 1. Here is negative 1. So the two sheets hyperboloid like this. And another quadratic surface is cones. So you can have x power 2 plus y power 2 equals z power 2. So you only have the power 2 terms. And this is cones. And also this one is paraboloids. A paraboloid is like here. So its mathematical equation is here. So x power 2 divided by 2p plus y power 2 divided by 2q equals z for pq greater than 0 times p times q greater than 0. So this is elliptic paraboloid. Elliptic paraboloid, the figure is like here, like here. So its range, you can see when p greater than 0, q greater than 0, you can see for z, for this coordinate, it can tend to infinity, right? For x and y coordinate also can tend to infinity, but for z can tend to positive infinity. You cannot to be negative value for z. Okay, symmetric property. So it is symmetric with respect to XOZ plane, right? And also YOZ plane. And it's symmetric to the z-axis. So now we consider its conic section. So if you use a plane to intersect with this paraboloids, one-sheet paraboloids, what can you get? So if z equals z1 greater than 0, you will get this one. So this one is just, this is ellipse. This is ellipse, you just get ellipse. And if y equals 0, if you use this plane to intersect with this one sheet, to intersect with this elliptic paraboloid, you can get is x power 2 equals 2pz. So this is a parabola. Okay, so for this conic section, you may get is a parabola or you may get is ellipse. And this is a hyperbolic paraboloid. Hyperbolic paraboloid is like this. So z equals x power 2 divided by 2p minus y power 2 divided by 2q. Here we also require pq greater than 0. So you can see the range of this different coordinates, right? So x can tend to infinity, y can tend to infinity, and z can also tend to infinity, from minus infinity to infinity. And you can see it's a symmetric property. Okay, and its conic section is like here. When z equals z0 does not equal to 0, you can get this conic section. So this conic section is a hyperbola, right? Hyperbola. And when x equals x0, you can get this conic section. It's also a parabola. Now we see this example. Specify the type of the quadratic surface z equals fxy equals x times y. So just from this equation, it's not in the standard position, so we don't know which figure it is. So we first write this matrix A here, and we transform. We want to transform this x times y as in standard position. So we first calculate its eigenvalues. We get the eigenvalue lambda 1 equals 1 over 2, lambda 2 equals minus 1 over 2, and then there exists orthogonal transformation x equals c times y such that z can be written as this one. After z, write in this one, so we can know this is a hyperbolic paraboloid. Now we have this principal axis theorem, corollary 6.4.7. So this is diagonalizable for real symmetric matrix. If A is a real symmetric matrix, then there is an orthogonal matrix U that diagonalizes A, that is U transpose times A times U equals the diagonal matrix, where D is diagonal and U is an orthogonal matrix. And we also have this theorem, 6.6.1, principal axis theorem. If A is a real symmetric n by n matrix, then there is a change of variables U equals Q transpose X such that X transpose A times X equals U transpose D times U, where D is a diagonal matrix. So we can transform this quadratic term to a simpler form. Okay. Now, we consider definite quadratic forms. A quadratic form fx equals x transpose times a times x is said to be definite if it takes only one sign as x variables over all non-zero vectors in Rn. Okay, the form is indefinite if it takes values that differ in sign, can be positive, can be negative for different x. And the form is positive definite if x transpose times a times x is greater than 0 for any x non-zero in the Rn space. And the form is negative definite if x transpose a times x equals 0 for any x does not equal to 0 in the Rn space. And if fx equals x transpose times a times x is greater than or equal to 0 and assumes the value 0 for some non-zero vector x, then fx is said to be positive semi-definite. And if fx equals x transpose a times x is smaller than or equal to 0 and assume that the value is 0 for some non-zero vector x holds, then fx is said to be negative semi-definite. So for the quadratic form, we like to consider it's definite or indefinite. If it's definite, you consider it's a positive definite or negative definite or positive semi-definite or negative semi-definite. And for definite matrices, so this is an important type of matrices. A real symmetric matrix A is said to be positive definite if x transpose A times x is greater than 0 for any non-zero vector in Rn. And it is negative definite if x transpose times a times x is smaller than 0 for any x non-zero vector x in Rn. And positive semi-definite if x transpose times a times x is no less than 0 for any x belong to Rn. And negative semi-definite if x transpose a times x is no less than 0 for any x belong to Rn. And indefinite if this quadratic form x transpose times a times x can take values that differ in sign, can be positive, can be negative. Okay. And we have this theorem 6.6.2. Let A be a real symmetric n by n matrix. Then A is a positive definite if and only if all its eigenvalues are positive. So you can see the proof on page 316.